All right, trig functions and graphs, lesson 10, last lesson in this unit, modeling sinusoidal functions. So we all know sinusoidal functions can be both a sine and a cosine equation, and it's really just that wave periodic type situation that we have. And then we're going to skip the review part. We're going to go to the first example. So what this lesson's all about is they give you a situation and you need to come up with the equation first of all, and then probably answer some follow-up questions. On this first one, they've given you sort of the graph. They haven't scaled the axes, but they've given you an idea of what it should look like. And let's take a look at this. So a nail is caught in the tread of a rotating tire at point N in the following sketch. So this circle is the tire and the nail is here. So the height, if you check out the y-axis, the height of that nail in centimeters, it would increase until it reached basically the top of the tire, and then as the tire rotated around, the nail would reach basically ground level, which would happen right here. And so what the horizontal axis is time in seconds. So it would take basically this amount of time to here for it to reach the ground and then back up to the top of the tire. Okay, let's see if we can scale the axes based on the information that they give us next. The tire has a diameter of 50 centimeters. So diameter of 50 centimeters, okay, from there to there is 50. So that tells us that our top value here is going to be 50, and when it's right on the ground, 0. And of course the midpoint then, or the midline, would be at 25, half of that. Okay, and rotates at 10 revolutions per minute. Okay, well that's a little bit trickier. So first of all, a revolution would be, think once around the unit circle, would be 2 pi, or 360 degrees, but we're going to stick with radians because this is an application question. Okay, so there's 10 revolutions per 60 seconds. Let's go with seconds. Okay, so if we kind of go, let's see, divide that by 10 on top, divide by 10, divide by 10, we can reduce that to actually 1 revolution would be equivalent to 6 seconds. So in other words, it takes 6 seconds for it to rotate once. So that means if we start here at the midline, when it returns back up to that point there, that should have taken 6 seconds. Okay, follow through another cycle, to here. That would be another 6 seconds, so this would be 12 seconds. Okay, now we know halfway to 6, this point here, would be 3. And then halfway between 3 and 6 would be 4.5. Halfway there would be 1.5, half of 3. Okay, and then just keep going like that. So halfway again would be 9 between 12 and 6. Halfway here again would be 7.5. And then finally 10.5. And there we go. Okay, that scales it pretty well. After 4.5 seconds, the nail touches the ground. Hey, that's what we got too. Cool. Okay, so use the information to write a scale. Done. Okay. Determine the equation for the height of the nail as a function of time in the form. Okay, so we did this already on lesson 8, where we came up with the A, the B, and the D, and actually C on some, for a graph. So I want you guys to try this one. Remember, we need to find amplitude, our period from this graph, and therefore after the period we're going to find the B value, right? 2 pi over the period, and our D value, or our vertical displacement, we'll call it. Okay, so you guys give that a try and then come up with your equation. All right, and I'll do that as well, and we'll check back and see if we have the same answer. So pause your video, please. Okay, so amplitude would basically be half the total range. Half of 50 is 25. There we go. Or you can go max minus the min divided by 2. Period, the length of one cycle, we already determined to be 6 seconds. B, 2 pi over our period, so that would reduce to pi over 3. And vertical displacement, which is our midline, okay, would be, you can calculate it by going max plus the min divided by 2. It's finding your average. Or you can kind of look at it and go, oh, the midline's at 25, so we were displaced up 25. Okay, throw everything in our equation. Please note that we are doing a sine graph, so that is our cosine function. And there we go. That's what we should get. Now they have a follow-up question. How far to the nearest tenth of a centimeter is the nail above the ground after 6.5 seconds? So think about what they're giving you. 6.5 seconds, that sounds like time is going to be 6.5. And how far is the nail above the ground? So that's height. We're looking for height. So let's take our equation, put 6.5. So h at 6.5. 25 sine pi over 3 times 6.5 plus, and oh, sorry, too many brackets, and then plus 25. Now, if there was another follow-up question where they were asking for, say, the t-value giving us h, and we have to graph it, I would definitely put this in the graphing calculator and get the graph. But since it's just one question and they're giving us t, asking for h, I would just simply put this in the calculator. Make sure you're in radian mode, okay? And you would just type in 25 sine bracket pi divided by 3 times 6.5 plus 25. Okay, so you go do that, and I'll do it as well. We'll see if you get the same answer. Okay, so typing that into the calculator, I'm in radian mode, and yeah, it's all good, same as the equation. I should get 37.5. Okay, now let's look at our graph to see if that's reasonable, and that's centimeters. So after, what did they say, 6.5 seconds? So that might be, I don't know, somewhere in here maybe. We got a height of 37.5. Okay, well that's somewhere between 25 and 50. I guess we did that right. Okay, good job. Let's look at the next page. Okay, example 2. This is one of my favorite examples because it's discussing the original Ferris wheel, which is really cool. So the first Ferris wheel ever built was created by a bridge builder by the name of George W. Ferris in 1893, hence the name Ferris wheel. The diameter of the wheel was approximately 76 meters, and the maximum height of the Ferris wheel was approximately 80 meters. You know what that means? That Ferris wheel was about the height of a 26, 27-story building. Is that crazy or what? In 1893. Okay, now the wheel had 36 wooden carts. See these carts down here? And each of those carts held 60 people. So you know what that means? If this was fully loaded, there would be 2,160 people on this Ferris wheel. Crazy, in 1893. It's amazing what they could do back then. Okay, so the Ferris wheel was introduced to the world in the 1893 World's Fair in Chicago. Very cool. Okay, so that being said, we now have to kind of draw it. All right, so if the wheel rotated every 9 minutes, oh wow, that wasn't moving too fast, was it? So every 9 minutes it went all the way around, kind of like, I guess, like the London Eye now, right? Use the data in the table to sketch a sinusoidal graph which represents the height of the car in meters as a function of time in minutes. Okay, so they've labeled our axes for us. Very nice, because usually you don't get that. Assume that the car is at the lowest point at time 0. Okay, so at the lowest point, what are we going to be at? They actually give that here, but if they didn't, we know highest is 80 meters, but the diameter is 76. So really that bottom cart is about 4 meters off the ground. So the lowest point would be right here at 4. Okay, and that's where we're starting at time 0. All right, now it rotates every 9 minutes. So after 9 minutes, it would be back down to that height of 4. Which means halfway between 0 and 9, so 4.5 minutes, should be at its maximum height of 80 meters. Okay, so that would be at 4.5. All right, halfway, so halfway between bottom and top, halfway to 4.5 would be 2.25. And we'd be halfway. What's halfway? Okay, so 80, this is where we're finding our d value to get the halfway mark. 80 plus 4 divided by 2 should give us 84 divided by 2, which is 42. So 42 is our halfway, occurring after 2.25 minutes. Okay, go another 2.25 this way, and we should have a point somewhere in here. Okay, let's see if we can draw a graph here. Make sure when you come to this bottom point, you don't just go straight at it, you kind of angle out and then join up with it. That way it doesn't look like a V. Okay. Okay, that looks good. One complete cycle, we've got it drawn. Guess what we're doing next? Just guess. Okay, yeah, that's right, we're getting the equation. Okay, this time it's a cosine function. Okay, so, and we have a phase shift. Okay, good to know. And remember with a cosine function, if we're looking for phase shift, we're looking at where that peak used to be on the y-axis. So notice our peak is here. All right, so why don't you guys get the equation for this? Go about getting our amplitude, our period, our b value, the phase shift, horizontal phase shift, and our vertical displacement, and then come up with the equation. Okay, so you guys work on that. I will as well. Pause your video. Okay, so we found our amplitude, 38, period 9, and then b follows from that, 2 pi divided by the period, so 2 pi over 9. Horizontal phase shift, our peak, we're looking for our peak because it's a cosine graph, was shifted to the right 4.5 minutes. And vertical displacement, our midline was at 42 meters, so up 42. Get our equation, so hopefully you got the same equation that I did. Now the follow-up questions. There's always follow-up, right? How high to the nearest meter is the cart 5 minutes after the wheel starts rotating? So we could just put 5 in for t, throw it in the calculator, but since the next question asks how many seconds after it starts rotating does it first reach 10 meters, which is our height, we're going to have to graph it to do the next part, so why don't we just graph it to do this, okay? So go ahead, bring up your calculator, put this equation in your calculator. Window settings, you can actually use your window settings from your graph, would be the easiest, okay? Take a look at your graph, and I'll do that as well, and then we'll answer those last two questions. Okay, pause your video. Okay, so we should have our graph looking something like that. If yours is not looking like that, first thing you check is your mode. Okay, we're in radian mode, that's good. Okay, then check your y equals to make sure that you typed it in correctly. So 38 cos bracket 2 pi divided by 9. Don't really need brackets around that because if you did put brackets and end it here, you would actually be only doing the cos of 2 pi over 9, so don't do that. Begin a new bracket, x minus 4.5, end bracket, plus 42. So the 42 is outside the cos. Okay, now window settings. I set them according to what we have on our graph, 0 to 9, 0 to 90. Could have gone 80 too, I suppose. And then take a look at your graph. Good. So that question was, how high is it 5 minutes after it starts moving? So if we go trace, type in 5 for x, and we get 77.7 meters. Okay, let's go back and write that down. To the nearest meter, so that would be 78 meters, wouldn't it? Okay, 78 meters. How high to the nearest meter? Let's see if that's reasonable on our graph. So 5 minutes. Yeah, it'd be pretty high, so that's reasonable. All right, so now last question. How many seconds after the wheel starts rotating does the cart first reach 10 meters? So kind of looking at our graph here, 10 meters is about in here. We would expect to be getting a value just a little less than 1 from this question. Let's bring up the calculator. Okay, we are therefore going to be putting 10 in y2 because they're giving us really the y value or the h value. So 10 in y2. Okay, so there's the graph. There's where it would first be reaching a height of 10 meters. So we want to find that intersection. Second calc, intersect. First curve, second curve, hit enter. For guess, you get to hear me tap again. Tap, 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 tap. Go far over, there we go. Enter. Okay, so take a look at our value, 0.8159. I said a little less than 1, right? There we go. And they want it to near a second. Oh, near second, haha, trick. Okay, our time is in minutes, right? And what we just got there was 0.8159 minutes. So 0.8159 yada yada minutes. They want near second. We need to change that into seconds. Oh, so let's do that and pause your video. Okay, so we should have gotten 49 seconds and we're out of time. Hopefully you're all good to go.